Welcome to Brain Vision.
This is the solution to problem 27, chapter 24 of college physics. Now, in this problem, we're asked to problem where we found that there was a wave that had a period of 10 to minus 16 seconds, and it had a maximum electric field amplitude of 3.0 times 10 to the 6 newtons per coulomb. Right. So this is our starting point, and first we're asked to find the frequency of the electric field density or energy density. And the thing is that this oscillation of the energy that they depend on the field squared. So U, remember, is epsilon 0 times E squared, which is equal to 1 over mu 0 times B squared, where E and B are the waves squared, and epsilon 0 is the negativity of vacuum, and mu 0 is the negativity of vacuum. So if you square the function, then this is what it's going to look like roughly, as in this diagram. So you have an electric field denoted by this black curve that is oscillating with a period of t. But at the same time, the energy density of this electromagnetic field is going to go as a sine squared function or a squared function. So what happens is that it peaks, the density peaks at a quarter of the period, then it goes to the wave, and then it peaks again at 3 quarters of the period and goes to 0 again at t. So you can see that this is basically, this blue dashed line is oscillating twice as fast as does the black curve. And so the period of the energy density is going to be half times the period of the field itself. So this is going to be 0.5 times 10 minus 16 seconds. And if we convert this to a frequency, then F is going to be, let's see, so this is 5 times 10 to the minus 17 seconds. And so F is going to be 1 over Tu, or Fu is 1 over Tu. This is going to be equal to 1 divided by 5 times 10 to the minus 17. And this gives us, this is 10 to the 17. So this is 0.2 times 10 to the 17 hertz, which is equal to 2 times 10 to the 16 hertz. So this is the frequency of the oscillation of the density stored in the electric field of radiation. Now, since you can equally well write this as the energy density in terms of E squared or B squared, and we know that the electric and magnetic fields in the electromagnetic wave are increased, we know that F of U is a general thing. So if the frequency of oscillation for the electric field energy density is something, let's call it Fu, then we know that the frequency of the energy density in the magnetic field is going to be the same. So it's also 2 times 10 to the 16 hertz. All right. So much about the frequency of the energy densities. Next, see what the maximum energy density is that's stored in the wave. So for that, we're just going to use U max is given by, let's just use the electric field, so it's epsilon 0 times E max squared. And so if you use 3 times 10 to the 6 Newton per coulombs for E max and 3 times 10 E, and 85 times to the minus 12 for per meters for epsilon 0, then this works out to be roughly 80 joules per meters cubed. So that's the maximum energy density. What about the minimum energy density? Now, this is going to be epsilon 0 times E min squared. But of course, the minimum is going to occur when the electric field goes to 0. At the same time, the magnetic field is also going to go to 0. So the energy density in the fields is going to be 0 in total. So this is 0 joules per meters cubed. Or not lastly, but in part E, we're asked to find what the average energy density is. So E is asking what U bar is. And so this is just a half of U max. And the fact, or the reason behind this, so this is 40 joules per meters cubed. And the reason behind this is that you're actually taking a time average of this sine squared function. And so when you do that, it actually works out to give you roughly half of the value of the maximum. So the average density stored is just going to be the average of the area under the blue curve. And you can find this by writing a waveform. So if you wrote E as something like E max times, let's say, sine of 2 pi over t times little t plus or minus 2 pi over lambda times x, and you would integrate the square of this function over one period. So you would write something like the average E squared is going to be the integral from 0 to t of E max squared times d little t sine squared of this argument. And if you work this out, this is actually just a half times E max squared. And so the result here is a half E max squared. And so this is the reason why the average energy density is half of the maximum energy density. And then lastly, the intensity of the wave is. So in F, we're asked to find what the intensity is. And the intensity is just given by the average energy density times C. And so this is 3.00 times 10 to the 8 meters per second times 40 joules per meters cubed. And this is going to be equal to, let's see, so this would be 120. So that's 120 times 10 to the 8 joules per meters squared times seconds. So this is 1.2 times 10 to the 10 watts per meters squared. So that's the intensity.